Swayam Prabha. Digital India. Educated India.
Now next topic is probability and distribution. It is more interesting and relevant to AI and ML. First let us see the introduction, the construction of the probability space. The theory of probability aims at defining a mathematical structure to describe the random outcomes of experiments. So, for example, when tossing a single coin, so we cannot determine the outcome, but by doing a large number of coin tosses, we can observe regularity in the average outcome. So, that is the meaning of the construction of the probability. Now, this unit actually consists of construction of probability spaces, discrete and continuous probability. Now, under the heading of the probability, we have to discuss this, and we have a subunits, that is sum rule and product rule and Bayes theorem related to Bayes theorem, summary statistics and independence related to independence, and Gaussian distribution corresponding to Gaussian, and conjugation and exponential family related to exponential topic, change of variables and inverse transformation in terms of the inverse transformation topic, and followed with this we have a optimization technique, and then the optimization is subdivided into continuous optimization using the gradient descent, and we based on the Lagrange's nonlinear equations, we have a constraint of optimization and Lagrange's multipliers, and based on that convex optimization and some more problem we may discuss. Now, we have to understand the flow chart of construction of a probability space, and you collect the data, and from the data find the mean and then variance. Based on the mean and variance, we have a summary statistics. So, that the summary statistics based on the topic of random variable and distribution. Once you know the random variable and distribution, the property related to summary statistics, and based on the function of the random variable, we have to transform and check it out the independency, and corresponding random variable distribution, and we have to find out the similarity. So, already we come across the inner product, that also we can apply into the random variable, and we have to incorporate with the property, and we need some sufficient statistics, and based on that whether it is a finite, then we have to go to the exponential family. In terms of the mean and variance of the statistics, and we have a probability of Bayes theorem. So, product rule related to Bayes theorem, and then sum rule related to Bayes theorem, and then based on the product and sum rule also is associated with the random variable and distribution. And once you know this, we can incorporate it with some Gaussian distribution, and then along with that we have to explain the examples, and related to Bernoulli random variable and distribution with example, and based on that conjugate and beta distribution. Once you know all these ideas, start from the Bayes theorem, you have to do the regression. So, Gaussian distribution finally end up with a dimensionality reduction, and Bayes also related to dimensionality reduction. Once you know Gaussian distribution, then density estimation we can evaluate. So, this is the flow chart of construction of a probability space. If you know the topography of this, you can understand the concept of related to random variable and probability distribution. Now, philosophical issues. When constructing an automated reasoning system, classical Boolean logic does not allow us to express certain forms of plausible reasoning. Consider the following scenario. We observe that A is false. So, we find B becomes less plausible. Although no conclusion can be drawn from classical logic, so we observe that B is true, it seems A becomes more plausible. We use this form of reasoning daily and we are waiting for the friend and consider the possibilities. H1, she is on time. H2, she has been delayed by traffic. And H3, she has been abducted by aliens. Now, when we observe our friend is late, we must logically rule out H1. We also tend to consider H2 to be more likely, though we are not logically required to do so. Finally, we may consider H3 to be possible, but we continue to consider it quite unlikely. How do we conclude H2 is the most plausible answer? Now, seen in this way, the probability theory can be considered a generalization of Boolean logic. In the context of machine learning, it is often applied in this way to formalize the design of automated reasoning systems. Further, arguments about how the probability theory is the foundation of reasoning system can be found in Pearl. So, in the year of 1988, so it is developed corresponding to the foundation of the reasoning, that is the philosophical issue of the probability. Now, Jaynes identified 3 mathematical criteria which must apply to all plausibilities. In the year of 1922 to 1998, the degrees of plausibility are represented by real numbers. The numbers must be based on the rules of common sense. The resulting reasoning must be consistent with the 3 following meanings of the consistence. They are consistency or non-contradiction, when the same rule result can reach through the different means. The same plausibility value must be found in all cases. Number 2, the honesty. All available data must be taken into account. Number 3, reproducibility. In our state of knowledge about the 2 problems are the same, we must assign the same degree of plausibility to the both of them. So, these are all the 3 reasoning, and that should be consistent. Now, Cox-Jaynes theorem proves that the plausibility to be the sufficient to define the universal mathematical rules that apply to the plausibility P up to the transformation by an arbitrary monadic function. Crucially, these rules are the rules of probability. Now, some machine learning text on probability models use lazy notation and jargon, so which is confusing. So, this text is no exception. Multiple distinct concepts are all referred to a probability distribution, and the reader has to often disentangle the meaning from the context. One trick to help make sense of the probability distribution is to check whether we are trying to model something categorical, that is a discrete random variable, or something continuous in a continuous random variable. So, the kinds of question tackled in machine learning are closely related to whether we are consider categorical or continuous models. Now, we are going to the deep of probability and random variables. Now, let us start with the sample space. Sample space is the most important, right? It means you take any event anything, and the set of all possible outcomes of an experiment. Take an experiment, all possible outcomes of an experiment is called as sample space and is denoted by omega. For example, you take a two successive coin tosses. So, what happened? Head will come, tail will come, head will come, tail will come. So, here H stands for tails, so H stands for head and T stands for tails. So, keep it in mind this, tossing a two coin, the possibilities of outcome is like that. Based on that, how many head we can choose, how many head will come, either one head will come or at least one head will come or no head will come or at least one tail will come. These are all the question may rise. Based on that, we move to the next step, event space A. The event space is the space of potential result of the experiment. So, a subset A of the sample space omega is the event space if at the end of the experiment we can observe whether a particular outcome omega, small omega in capital omega is in A. So, the event space A is obtained by considering the collection of subset of omega. For the discrete probability distribution, A is often the power set of omega. So, that is the meaning of event. So, head only, tail only or in the sample space anything may get it, then it is said to be event. Next, we have to discuss the probability. Probability means you take an event A in A and associate it with what P of A mean, probability or degree of an event, then P of A is called probability of A, mean total number of outcomes you know, number of possibilities you know. These two are important to identify the requirement of the probability. Now, the probability of single event must be in the interval 0, 1. So, all are tail. Suppose you take a coin, tossing a coin, probability of getting head is 1 by 2, probability of tail is getting 1 by 2. Suppose both face is the same tail, then probability is 1 and then there is nothing face in the head, therefore 0 will come, therefore maximum interval is what? Upper bound 1, lower bound is 0. So, the probability of overall outcomes in the sample space must be 1. Therefore, P of omega equal to 1. So, given the probability space omega AP, we want to use it to model some real world phenomena. In machine learning, we often avoid explicitly referring to the probability space, but instead refer to the probabilities on the quantity of interest. So, we denote by T, we refer T is a target space and refer to the element of T as a states. So, we introduce the what mapping from sample space to T referred to the target space and X is the what introduction of the function. So, X of omega equal to T and it takes the element omega and outcome and returns a particular quantity of interest X, the value in T. So, this association mapping of omega to tau is called as random variable. So, random variable is nothing but what? X such that omega maps to T, then this implies what? X of omega. So, this way we have to start with the random variable. So, let us go with one example. In the case of tossing two coins, counting the number of heads. So, random variable X maps the three possibilities of the outcomes, either head or head tail or tail head or tail tail. So, in the random variables x of HH. What is h of x of HH is mean 2 head, and x of HT is 1 head, x of TH is 1 head, and T of T is no head, therefore 0. So, in particular case, then the T values are what? 0 head, 1 head and 2 head. So, the possibility of the element T we are interested in. So, this is the meaning of random variable corresponding to the function. Once you can understand the beauty of random variable, let us go with the next ideas. He is called it as sample space omega and finite t. The function corresponding to random variable is essentially that look up the table, and S is a subset of t. We associate with what? The subset S of probability of random variable x belongs to the closed interval 0, 1, and the particular event occurring the corresponding to the random variable, and followed with the example provide the concrete illustration of the terminology. Therefore, consider a statistical experiment where we model a unfair game consisting of drawing of 2 coins from a bag with replacement, that is the condition. Now, there are coins from USA denoted as a dollar, this symbol, and UK denoted by pound in the bag, and since we draw 2 coins from the bag, there are 4 outcomes in the total. The state space or sample space omega of this experiment is what? Dollar dollar, dollar pound, pound dollar, pound pound. So, let us assume that the composition of the bag of coins is such that draw returns at a random a dollar with a probability of 0.3. So, this is the statement, and this is the meaning of possibilities of the experiment associated with dollar and pound. Now, further explanation of event or interested in the total number of times the repeated draw returns dollar. Let us define a random variable x that maps the sample space omega to t, which denotes the number of times we draw a dollar out of the bag. So, we can see from the preceding sample space we can get 0, dollar, $1 and $2. Therefore, the samples random variable corresponding to outcome is t is either 0 or 1 or 2. So, it may be $0, $1, $2 and vice versa in the pound. So, the random variable x can be represented as a table in the following manner: x of 2 possibilities of the dollar, no pound, then we have the value of 2, and $1, 1 pound is 1, 1 pound, $1 is 1, and no dollars, all are pound, then the value is 0. So, according to your expectation, we have to design the what? Random variable, so that you can understand how the random variable is generated. Now, we return the first coin, we draw before drawing the second. This implies that the 2 draws are independent of each other, which we will discuss in the rest of the section. Note that there are 2 experimental outcomes which maps to the same event, where only one of the draws returns in the dollar. Therefore, the probability of mass function of x is given by probability of x equal to 2 is equal to probability of dollar to dollar. So, it means it is independent, therefore, probability of dollar into probability of dollar. So, the possibilities of probability of dollar is 0.3 and 0.3 multiply, it becomes 0.09. Okay. Now, if you have a probability of x equal to 1, it means either S dollar will come or dollar S will come. So, if it is union, then you have to put a plus, and then probability of S dollar plus probability of dollar S is nothing but one is getting a probability of dollar is 0.3 and getting a pound is 1 minus dollar is 1 minus 0.3. So, similarly P of a pound and dollar is probability of pound is 1 minus probability of dollar, that is 1 minus 0.3 into probability of dollar is 0.3, and then 1 minus 0.3 subtract and multiply with 0.3. Similarly, 1 minus 0.3 into 0.3 multiply, add them, the resultant is 0.42. So, you can get the probability of x equal to at least $1. Now, the probability of no dollar occur in the sense that probability of pound. So, probability of pound comma pound is probability of pound into probability of pound because independent. Therefore, probability of pound is 1 minus probability of dollar. So, 1 minus dollar is 1 minus 0.3. Similarly, probability of pound is 1 minus 0.3. If you together multiply, you have 0.49. So, this way we can get probability of mass function. I hope you can understand what is the meaning of mass function. Now, let us go discrete and continuous probability. When the target space T is discrete, we can specify the probability that random variable x takes the values x in T and is denoted by probability of x equal to x. So, the expression probability of x equal to x for a discrete random variable is known as probability of mass function. So, when the target T is a continuous, then for the probability mass function will be generated. When the target space T is continuous, then the real line R, it is more natural to specify the probability of the random variable x in the interval. So, it is denoted by probability of A less than or equal to x less than or equal to b, means probability of A and probability of b is the extremities in between the bounds of A and b. This statement is true if A is less than b. By convention, we specify the probability of the random variable x is less than the particular value x and is denoted by probability of x is less than or equal to x. So, the expression probability of x is less than or equal to x is a continuous random variable x is known as cumulative distribution function. Next, we discuss the continuous random variable related to this. Now, we have a note. So, we will use the phrase univariate distribution to refer to the distribution of the single random variable whose states are denoted as non-bold x. Now, we refer to distribution of more than one random variable as a multivariate distribution, and we usually consider the vector random variable. So, whose states are denoted by bold small x. Now, we are going to discuss the discrete probability. So, the figure 6.2 illustrates the probability mass function denoted by PMF. PMF stands for probability mass function or discrete probability distribution. So, you take two random variable x and y. The probability array of numbers in the figure 6.2 shows an example. So, the target space of the joint probability in the Cartesian product of the target space of the each random variable, we define the joint probability as the entry of the both values as probability of x equal to xi and y equal to yj is equal to nij by n. So, this is the meaning of discrete probability. So, it means jointly we have to distribute x as well as y. So, x as well as y is a two random variable we have to use at a time, and here nij stands for the number of events with the state xi and yi, and n is the total number of events, and the joint probability distribution intersection of both the events, then probability of x equal to xi and y equal to yj is nothing but probability of x equal to xi intersection y equal to yj. Here x is small x and y is small y is lazily written as probability of x comma y is called the joint probability function. So, this is most important for joint distribution of the function, and one can think about that probability function takes the state. So, this is the picture, that is earlier I said the visualization of discrete bivariate probability function and with respect to the x as well as y, and this diagram is adopted from the book from Bishop 2006, and then x1, x2, x3, x4, x5 is a corresponding x random variable corresponding to mapping to the y1, y2, y3, and then the probability of xi comma yi we have to do with the joint probability distribution function, and it is a marginal probability function with irrespective of the random variable y and written in the p of x. Now, x is associated with p of x, mean the random variable x is distributed to the probability of p of x, and consider the instance small capital X equal to small x, then the function of the instances call it as a conditional probability for which capital Y equal to y is written as p of y by x. So, y depends on x, that is called it as conditional probability function. Now, let us go with one example. Consider two random variable x and y, where x has 5 possible states and y has 3 possible states, that is already shown the figure 6.2. We denote by nij is the number of events and written as capital X equal to xi and capital Y equal to yj, and we denote the number capital N. So, the value Ci is the sum of the individual frequency of the ith column, and Ca equal to summation j equal to 1 to 3 Nij. So, similarly, if you take Rj summation I equal to 1 to 5 Nij, mean Rj is the row sum, and using this definition we have the distribution of x and y. Now, we have a distribution of each random variable. So, the marginal distribution can be written as probability of x equal to xi, which is equal to Ci by n, where summation j equal to 1 to 3 Nij by capital N, and a probability of y equal to yj equal to rj by n equal to summation I equal to 1 to 5 Nij by n. Now, where Ci and rj are the ith column and jth row of the probability table respectively, by convention for a discrete random variable with a finite number of events, we assume that the probability sum up to 1, probability of x equal to x1, x equal to x2, x equal to x3, x equal to x4, x equal to x5, sum them, maximum probability value is 1. Similarly, corresponding to y, probability of y equal to y1 plus probability of y equal to y2 and y3, sum them, the maximum is 1. So, the conditional probabilities, one depends on the other. We have a conditional probability is a fraction of the row or column in a particular way. So, for example, the conditional probability of y given x is p of y equal to yj divide x equal to xj, mean y depends on x, and then the value is nij by ci, and nij is corresponding both probability joint distribution of the outcome of the favorable divided by ci, and related to conditional probability of x is or given y is related to nij by rj. So, in machine learning we use the discrete random probability distribution function to model the categorical variables. So, the variables take a finite set of unordered values. So, they could be categorical features such as the degree taken at university when used for predicting the salary of a person, or categorical labels such as letters of the alphabet when doing handwriting recognitions. So, these are all the some examples in terms of the machine learning we can use the conditional probability. Now, we are going to idea of about the continuous probability theory. So, we consider a real valued random variable in this section. We consider the target space that are intervals of the real line R. So, in this talk we pretend that we can perform operation on real random variable as we have a discrete random variable probability spaces with the finite states. However, this simplification is not precise for two situations. So, when we repeat something infinitely often and we want to draw a point from an interval, the first situation arises when we discuss errors in the machine learning of the following chapters. So, the second situation arises when we want to discuss the continuous distribution such as the Gaussian. For our purposes, the lack of precision allows for a briefer introduction to probability. So, note in continuous spaces there are two additional technicalities which are counterintuitive. First, the set of all subset is not well behaved enough. It needs to be restricted to behave well under set complements, set intersection and set unions. Second, the size of the set turns out to be tricky, and then the size of the set is called a measure, and the cardinality of discrete sets is one of the examples to do for measuring of this counterintuitive, and then this set is called it as a measure. For example, the cardinality of the discrete sets, the length of the interval in a real number, and the volume of a region is R D tuple or all measures, and this set behaves well under set operation and additionally have the topology or called Borel sigma algebra. So, Beaton details a careful construction of the probability spaces from the set theory, and without being bogged down the technology, and see the website https://tinurl.com and then /YB3T6MFD, you type it and we can see the more about that, how the Borel of sigma algebra is demonstrated. For a more precise construction, further you refer Billingsley in the year of 1995 published associated with Jacob and Proter 2004. These you refer, further you can understand the Borel sigma algebra. So, this is more important in machine learning, that is why the theory is most important. Once you may understand this, further we can interlink with this to the machine learning. Now, we consider real valued random variable with their corresponding Borel sigma algebra. We consider random variable with values in the R power d to vector of real valued random variables. So, let us start with the definition. probability density function, a function f such that r power d to r called a probability density function. Then the number 1, the condition is you take an x for all x in r power d such that f of x is greater than or equal to 0. So, r power d is a volume of the region, and you take an interval in the set of r. So, you take whatever may be the value of x in r power d, and f of x is positive, and we have a sum of this integral function integrand of f of x r d is equal to 1. So, this is called as probability mass function of a discrete random variable, and the integral 6.1 is replaced with the sum. So, you take an integrand of f of x with the operator x and sum them, the maximum value 1 will come. That is the meaning of integral r over d, mean volume of the region of f of x can be calculated. So, this is the meaning of probability density function. Now, we observe the probability density function is any function f that is non-negative and integrates to 1. So, we associated random variable x with the function probability of a less than or equal to x less than or equal to b equal to integral a to b f of x dx, where a comma b in real number and x in R is also outcomes of the continuous random variable. So, x belongs to R power d are defined analogically by considering a vector x in R. So, this associate called the law or distribution of a random variable x. So, this is the meaning of what? The function associated with the distribution of a random variable. So, you fix a and b according to your possibilities of the event, either it may be lies between 2 and 3 or 0 to 1 or something like that. You have to do take an event corresponding to fix the a and b can generate the what? Random variable. Next to note, in contrast to discrete random variable, the probability of continuous random variable x taking the particular value probability of x equal to small x is 0. So, this is like trying to specify an interval where a equal to b. So, if a equal to b, what happen? It becomes a to a, then it becomes 1 will come, maximum value 1 will come. Now, next definition is cumulative distribution function. A cumulative distribution function is denoted by CDF in the form of the multivariate random variable or real values random variable. F of x equal to x is probability of x1 less than or equal to x1 and so on xt less than or equal to xt, where x equal to x1 xt and small x is x1 xt, and the right hand side represent the probability of the random variable, and xi takes the value smaller than equal to x. So, the cumulative distribution function can be expressed the integral of the probability density function, that is f of small x of over the x is equal to integral minus infinity to x1 and so on the multiple integral and so on minus infinity to the xt of f of z1 z2 and so on zd of dz1 dzd. So, we have a note of the reiterate that there are the fact of two distinct concepts when talking about the distribution. First, the idea of PDF denoted by f of x, which is non-negative function that sums to 1. Second is a law of the random variable x that is associated with the random variable x with the PDF f of x. Now, we have a picture. This is a discrete because everything is separated minus 1 to 0 to 2, and we have a minus 1 and corresponding in between 0 to 1 and 1 to 2, and here 0 to minus 1, and these represent discrete distribution, and corresponding B represent the continuous distribution starts from 0.8 to 1.8 like that. Then we have a probability corresponding to discrete the domain to codomain is maximum of what, 0.8 to 1.8 like that, and we red line denoted by the corresponding continuously distributed. Here for A discrete distribution only one corresponding the value. So, that is the difference between probability of capital Z equal to small z and probability of x. So, these are all the two different category of distribution. One may understand that which one is a continuous, which one is a discrete, so that we can incorporate it with the what corresponding to machine learning ideas. Now, we consider two examples of the uniform distribution related to contrasting discrete and continuous distribution, where each state is equally likely to occur. So, the following is an illustration of some example, the difference between the discrete and continuous probability distribution. So, this is the picture corresponding to probability of z equal to z. When you take z equal to minus 1.1, the probability of z equal to 1 by 3. When you take probability of 0.3, corresponding probability of distribution mass function is 1 by 3, and 1.5 corresponding 1 by 3. So, now let us start with discrete continuous uniform random variable. So, we have a 3 state, one is minus 1.1, 0.3 and 1.5. So, we have a mass function can be represented with probability values. Alternatively, we think of this as a graph in the following figure, where we can use the fact that the states can be located on the x axis, and the y axis represent the probability of the particular state. So, this is the corresponding picture of these ideas. So, this is the picture corresponding to A and B, and then 6.3 is a discrete and 6.3b is a continuous, where we use the fact that the states can be located on the x axis and the y axis. So, this is the meaning of representation of discrete A, and we have the fact that states can be located on the x axis and the y axis represent the probability of particular state. The y axis in the figure 6.3a is deliberately extended, and then it has the same figure for the continuous in 6.3b. So, this is the demonstration of the picture corresponding to the figure. Now, we have a continuous random variable taking the values in the region 0.9 to 1.6 and represented the figure 6.3. So, observe that the height of the density can be greater than 1. Therefore, this hold when integral 0.9 to 1.6 p of x equal to maximum value is 1. Now, we have a type of two cases, one is point probability, another one is interval probability. For a discrete, we have to discuss with the mass function, whereas the interval it is not applicable for the discrete. For continuous, we have a probability density function, whereas in the interval we have a cumulative distribution function. So, note that this is the additional subject related to the function with regards to discrete probability distribution. So, the states Z1, Zd do not in the principle have any structures. So, there is usually no way to compare them, for example, of red, green, blue of the variable Z1, Z2, Z3 respectively. However, in many machine learning application, discrete state take numerical values, example Z1 equal to minus 1.1, Z2 0.3 and Z3 1.5, where we could say Z1 less than Z2 less than Z3. Therefore, the discrete states that assume numerical values are particularly useful because we often consider the expected values of the random variable. So, note we will be using the expression probability distribution not only for discrete probability mass function, but also for continuous probability density function. So, technically it is incorrect. In line with the most machine learning literature, we also rely on context to distinguish the different types of the phrase probability distribution.